Alright, and for this video, we're going to see how we can use the acid ionization constant to help us answer a problem dealing with a weak acid. So in this case, we've got some information. We've got an example here. Up here I have the general equations for acid and for Ka that we can refer to. In this problem, the concentration of acetic acid, which is HC2H3O2, is 1.25 moles per liter. What is the pH of the solution? If you're working on a problem like this, it'd be good, you need to make sure you reference your textbook. It's not page 511, it's actually page 747, believe it or not. There's a table with Ka values for a bunch of different acids. So I looked up this Ka value in the textbook. So what we want to do for this type of question, since acetic acid is a weak acid, is we want to set up an equilibrium expression. So we've got acetic acid dissolving to make H plus and acetate. 2 minus. And we're going to make an ice table, of course, because that's what we do. Hopefully by now ice tables are your best friends. So we want to know the concentration of acetate, hydrogen, and acetic acid at equilibrium. The question's asking us the pH, so what we're really interested in is the concentration of H plus at equilibrium. Alright, so I'm setting this up. So I'm just going to square bracket these where they are over here. And our initial concentration of acetic acid is 1.25 moles per liter. And we're imagining this is at the instant we put it in before it has a chance to ionize. When the ionization happens, there's a 1:1:1 ratio here. So this concentration will go down by some value x. These concentrations will go up by some value x. So 1.25 minus x, x, and x. We need our Ka expression to help us solve for x. So Ka is the concentration of the hydrogen ion times the concentration of acetate divided by the concentration of acetic acid, O2. So that will be x squared divided by 1.25 minus x. In this case, we may be able to make the assumption to ignore that x. So let's take a look at that. Ka, so it's 1.8 times 10 to the minus 5 equals x squared divided by 1.25 minus x. So just off to the side here, Ka times 1,000 is 1.8 times 10 to the minus 2, so that's 0.018. So that's smaller than our initial concentration, still by quite a bit. So I think we can safely assume that we can ignore this x over here. And then I will write 1.8 times 10 to minus 5 equals x squared divided by 1.25. Alright, so we're going to solve for x. 1.8 times 10 to the minus 5 times 1.25, and we'll find the square root. And my value for x that I get is 0.0047. So in this case, if I'm trying to find the concentration of hydrogen, so I can find the pH, the concentration of hydrogen ion at equilibrium is equal to x, is equal to 0.0047 moles per liter. And we can find the pH from that. It's a good idea to go back and check and see if your assumption was good. So maybe just over here, I'll square off a little area. I'm just going to make sure that the assumption looks like it was okay. This is a really good thing to do, because usually it is just fine. So x squared 0.0047 squared divided by 1.25 minus 0.0047 equals, so 0.0047 squared divided by 1.25 minus 0.0047 equals, and I get 1.77 times 10 to the minus 5, which is close enough to 1.8 times 10 to the minus 5 that I feel good about the assumption. So we finish off by finding the pH. The pH is minus log the concentration of H+, so 0.0047, 0.0047, and from that we'll have our pH, except I can't find the log button on my calculator, because that's what happens. Okay, and the pH I get is 2.3. 2.3 is the pH of a solution of acetic acid if the concentration of the acetic acid is 1.25 moles per liter. The other types of questions you may come across if you're working on this involve percent ionization. So this is where we look at how much acid ionized versus the amount of acid that you put in there in the first place. So we can use our answer from this question to find the percent ionization of acetic acid in water. So in this case, P equals the concentration of the acid that ionized, which in our example is X. Okay, so our ions are over here. So X is the concentration of the ionized ions. So that was 0.0047 moles per liter. 0.0047. And we're going to divide that by the concentration of the acid that we put in there in the first place, which was 1.25 moles per liter. And multiply that by 100. Alright, so let's see. 0.0047 divided by 1.25. And what we find is the percent ionization for acetic acid is about 0.38%. So that means if you put about 300 molecules of acetic acid into a solution, about one of them would actually ionize. So it's a pretty low percentage. There are problems that you can work on involving Ka and dissociation and pH. They can be found in your textbook on page 512 and also on page 514. So choose one or two questions from each of those pages and give them a shot.